Okay, so what I'm talking about here is an application to automatically generate computer code using a GPT-2 language model. And so my approach is based on the GPT-2 model developed by OpenAI, which is a precursor to GPT-3, and follows from a transformer-based language model. These have been very successful in modeling English language. The work is based on about 32,000 Python programs from GitHub, as made available by Google, and basically these models uh, generate a continuation of text, and in this case, a continuation of Python programs. The one of the interesting new things here is that I um, introduce some enhancements in prompting that allow specific tasks, including the generation of code that does specific applications. So I'll get to background later, perhaps, if I have time. So let's see here. So again, we're working with a transformer architecture. It's one way version of that, just using the encoder and masking future words and just looking at past words. It's introduced by OpenAI in 2019. I use their XL pre-trained model, which has about 1.5 billion parameters spread over 48 layers. And this involves using about 40 gigabytes of GPU RAM. So hence, I need to do model parallelism over multiple GPUs. And inference comes from a 6.5 gigabytes binary model. I'm using the Hugging Face implementation of GPT-2. It's a reverse engineered version. The data that I'm using is based, well, the original OpenAI data is based on Reddit posts. Those with three comma quality assessments to try to get a sense of good quality posts. That was never released, but it was sort of reverse engineered and released as open web text, which is a 40 gigabyte data set. So that's used to train the pre-trained model that Hugging Face makes available. And I continue that training using Python code. So that's considered fine tuning. The Hugging Face, the model is continued using data up to September 2019, and I collected it using Google BigQuery. And there's a lot of data, so I just took 1% samples of this data, 1% sample for training, 1% sample for evaluation, and held out another 1% for later testing. I tried to do something similar to the three comma filtering done on Reddit posts by looking for GitHub posts that had a watch event. They would be watched by someone more than twice, and I limited the code size to programs of less than 100K, which actually easily captures almost everything except for outliers. Analysis shows that 75 percentile of programs are less than about 6.5K. The big this is just an example of the query to get the data from BigQuery, and the result is a is put together by me into a sort of loose JSON format where there's basically one line per Python program, and that's the sort of content area here that's highlighted here. So again, about 32,000 programs are used for training. Most of the processing of the data is really quite simple. It just involves putting an end of text tag at the end of each program, a specific one that was defined in the GPT-2 model. And some people I've seen trying to do things with like beginning of text and end of text and other sorts of things, but actually it's not required and tends to produce worse results. The text isn't processed on a character basis. It's not processed on a word basis. It's processed on a word part basis. It's byte pair encoded, so it's broken up into word parts that are represented by in a 256 byte space, and combination of those word bytes sort of iteratively built up. Combinations of word parts, combination of words, and combinations of words. And the result is sort of a vocabulary of about 50,000 tokens. Training for this took about a day and a half, spread over four GeForce GTX 1080 Ti's with 11 gigabytes of RAM each. A lot more training could be done on this, probably several more days or maybe even weeks, but what I've done seems to work fairly well. That's what the machine looks like. The uh, the the actual layers are defined to be spread across multiple GPUs. So you see this sort of device map parameter here, and that shows you that, say, you have most of the layers. There are 48 layers, 0 through 47, and they're spread on GPU 0, 1, 2, and 3. A little bit less on GPU 0 because there's some overhead required for other parts of the model there, but the rest are sort of evenly spread. It's a little bit of the layers do talk to each other, so you can't really just break them any place, but this seems to work. Anyway, it allows 40 gigabyte models to be trained, which is quite big. Oh, and later I'll mention, say, some ways to do even better than that. So one of the key things about making these models work is to basically all these language models, they just basically continue text with likely continuations. The way to get them to actually do something is to trick them into continuing in a way that will solve an application. And these tricks are called prompts. And I like to say that they're analogous to, they're like the language model as SQL is to, say, a database. A carefully crafted prompt is to a language model. And if it's crafted properly, it will get the results you're looking at. So one of the key things that my prompts do that are a bit get the results I want is that I start the text to be continued with this shebang that indicates a shebang user bin env Python 3. That tells the language model, hey, I need to continue a Python program because that indicates a Python program. And then I include things like the libraries that I want to use, and that tells it what sort of domain of problems of code to look at. And then finally, one of the key things is that I have a comment. You'll see creates a plot X versus Y, and then the idea is, well, what follows that? It should be that particular action. And so create a plot. This prompt is designed to ask the model to create Python code that's going to plot X versus Y. We'll see if it works. There's some hyperparameters to consider in these cases. So let's see. Things like temperature, this is a statistical interpretation of it, but ultimately I like to characterize it as creativity. The higher the level, the more creative and diverse the set of potential outcomes is, and it sort of flattens the distribution with a high temperature, so there are a lot of possible outcomes that could happen. Things like top P, top K, and sampling means that well, say top P says it's going to take the 80th, in this case, 0.8 means that it's going to take 80% of the distribution of possible outcomes and sort of cut off at that point and select from within that 80 top 80% based on um, the distribution within that subset. You could also say take the top K, or like 100 most likely outcomes, and select from that based on their probabilities weights as well. It's a bit of there's no really clear cut way to do this, but it does create diversity in the potential outcome. Another little thing that I found that kind of works better with this is to use n-gram size of one rather than using combinations of words. It tends to work better with programs, but larger n-grams work better with human languages. Blocks of phrases work well in that case. So let's see what we get here. So yeah, the green stuff is what the GPT-2 model generates. So you'll see that wow, it generated plots and it had a label in there, and it creates a legend and a show. Um, so this is what it generated, and so what we've done is we've created something here that will generate code for us in Python using a language model. Um, and it's defined, and it happens because of the structure of the prompt. And it's very hard to evaluate whether these things are doing um, the right thing. But one of the most direct ways to evaluate is just to run the code. So here, if I just press run on this, if I cut and paste it into a cell in Jupyter Notebook and press run, it produces this graph. It works. Not only does it work, but it also adds, a legend and labels. It does as well as you would expect a human who was asked to take on this task. So that's quite impressive there. Um, so, how do you evaluate this stuff? Well, one possibility is just to generate a whole bunch of things and try running them, but that's a bit risky. But and seeing if they run or not. But it could run even if it does the wrong thing. So that also doesn't tell you anything. You could evaluate it in a Lambda style by trying to get it to predict the last token. But again, there are many ways to write English. There are many ways to write a program that works, even if the next token isn't exactly the same as the token in another example. But these sorts of evaluations are useful if you are going to compare multiple different versions of the same type of model to see which one might be producing better results. So maybe 15% accuracy is correlated with something that's better than something with 14% accuracy. So there you go. That's my model. I I'll take just a couple minutes to go and talk about background because it's kind of interesting, but I know I don't have a lot of time left. So I would point out beyond what is shown here, this is a rapidly evolving sort of space. So, the latest things are models that are well beyond what I've just shown, like the Google switch transformer with 1.6 trillion parameters. You could expect it to write Python programs much better. But other things to consider when doing this sort of thing are that there's something called a team called Aloofa AI that's created a sort of open version of the GPT-3 model database and is training and releasing open versions of that. So that's even better than the GPT-2 model that I used and open. But another consideration is that CPU capacity is a big problem, and so there's a tool called Deep Speed that can be used to basically compress the amount of memory required to train these models, so that you can, for instance, do on one GPU what I just did on 4 GPUs, or do an even larger model over 4 GPUs and run it faster. So that's something that's also really important to be aware of. Thank you very much.